Okay, hello everyone. My name is Alshandra Aurela Walangadi, or you can call me Alsha with my assistant lab code is AW. And today I'm going to give you guys a brief review of the module fourth and fifth of the electric circuit lab. And in this module itself, we're going to talk about superposition, Thevenin's, and also Norton's theorem. The overview of the materials that we are going to talk about is voltage and current division, superposition, source transformation, Thevenin's theorem, Norton's theorems, and also the correlation between Thevenin's and also Norton's theorem. So the first topic that we're going to talk about is voltage and current division. So this is more of a basic law or principle that we need to know about how voltage and current works in different configurations. As we know, voltage has the same value within, I guess, like two loads when they're in parallel, while current has the same value when it is in series. And voltage and current division itself helps us to find these values of voltage and current when they're in the opposite configurations, where voltage division is finding the voltage value of two or more resistors that are in series, then current division is to find the current value of two or more resistors that are in parallel. And the formula is, as you can see, is on this PowerPoint itself. You can follow the formula if you want to. And the formula is derived from Ohm's law and also the characteristics of voltage and current itself in different types of configurations. In voltage division itself, we got this formula from this. As we know from this circuit itself, it has a voltage supply, and it supplies two resistors that are in series, which is resistor 1 and resistor 2. As we can assume, between these two resistors, they would have the same current value because they are in series. So we can assume I, which is the current within the circuit, is V over R total, which is V over R1 plus R2. Next, it's just easy Ohm's law, where V equals I multiplied by R. Then we can count the voltage within R1 and R2, which is V1 and V2, by substituting the I from this first equation towards the Ohm's law. Then we get V over R1 plus R2 multiplied by R1 for V1, and for V2, this is going to change to R2. Sorry for the misspelling here. Next, we have current division. It's a bit different than voltage division. It's a bit more, not complex, but a different characteristic because we're going to acknowledge current here, not voltage. As we know here, we have a voltage source, and then it supplies to two resistors that are in parallel. As we know, current wouldn't have the same value when they are in parallel, but the voltage between resistor 1 and resistor 2 is going to have the same nominal. So then we can assume that V is going to be the same nominal. So if we multiply I1 multiplied by R1, it's going to be the same value to I2 multiplied by R2 because the voltage value is going to be the same. Then we can just rearrange to E1 equals to, not V equals. And then we have Kirchhoff current law in node A because the current is going to be divided into two segments, which is this segment here that has R1 and this segment here in R2. Because there's no way the current is going to be the same value. Maybe if we have the same value of resistors, but if it's going to be the different values here in R1 and R2, let's assume it's 5 ohms and 10 ohms, there's going to be a variation of the value of current itself. So we have this Kirchhoff current law, which is whatever current that comes in equals to whatever current that is coming out. So we see from the node A here that I is the current that is coming in the node A, and I1 and I2 is the current that is coming out of this node. Then we just substitute the I equation here to the I1 and I2 values that we had from the first equation. From this easy substitute, we get this formula, which is the same as this one. But you guys have to note that this formula isn't going to be the same when the resistors are going to be added. For example, if I have another resistor here in parallel, then the Kirchhoff current law equation is going to be different because the current is going to be divided within three sectors here. So there's going to be R3 here. So the equation itself is going to be a bit longer, and it's not going to be this simple. It's going to look a lot more like this part here, which is in yellow, which is 1 over R1 and 1 over R2, because current division is much more easier to be written in conductance rather than in resistance, because we are going to count how well the current goes within the load itself. That's why we use conductance for an easier counting or calculating. Okay, next is superposition. So superposition principles says that the voltage across, or maybe current, through an element in a linear circuit is the algebraic sum of the voltage across or current through that element due to each independent source acting alone. So the main reason why we use superposition is to analyze linear circuits that have two or more independent sources. Why it's much more easier to analyze with superposition is because we calculate the contribution of each independent source separately. So it seems maybe easier, but it doesn't always give you guys a much more shorter calculating time. So if it has two or more independent sources, sorry, more than two independent sources, it's going to be much more longer. To do superposition's law, as you can see in the notes here, we need to consider one independent source at a time, while all other independent sources are disabled. So when we have a voltage source and a current source, when we are going to analyze maybe the voltage or current in one of those sources, we need to disable one of the other sources that we aren't going to consider. And for dependent sources are retained because they depend on the circuit variable, so we don't deactivate the dependent sources. Okay, this is an example for you guys to understand more of this topic. So here we have a circuit, and we're going to use superposition theorem to find the V in this circuit. As we can see, it has two independent sources. You can see that it is in circles, not in a rotated square, kind of like a rhombus. A rhombus is dependent sources. When it's in circles, it's independent sources. So how we find the voltage value of the circuit is, first, we need to acknowledge all of the independent sources. As we can see, we have a current source here, 3 amps, and then we have a voltage source here in 6 volts. Then we will continue to find the value of V1 and V2. Why we have V1 and V2? Because there are two independent sources. If we have 3 independent sources, then we're going to find the V3 too, because we are going to sum all of the voltage that we find within each independent sources. So first, finding V1, I chose to turn off the 3 amps here. So we're going to have an open circuit. Then we can use Kirchhoff voltage law or mesh analysis or voltage division to find the voltage value within this resistor here. Then we get 2 volts, and then we need to find V2, which we are going to obtain by turning off the voltage source, which makes it an open circuit here. Oh, sorry, a short circuit here. Then we can use the current division and Ohm's law to be able to find the voltage value that is in this resistor itself, and we get 8 volts. Then we just add those two nominals, which is 2 plus 8 equals to 10 volts. And that is the algebraic sum of all of the voltages in each independent sources, which is 10 volts. And this is the total voltage that is in this resistor. Okay, next is source transformation. It's just a process of replacing a voltage source connected in series with the resistor to a current source connected in parallel with the resistor. As you can see here, we have a V source and an R in series. We can just change it to an E source to a parallel resistor, and we can just use Ohm's law to find the I or the V that we don't know. So example, if we have the V value here and the R value here, but it's much more easier to maybe calculate the circuit when it's in parallel, then we can change it by calculating the I, which is V over R. Then this nominal we're going to put here, and then we're going to change the configuration of the resistor when it was in series to parallel, and this works vice versa. So you can change the current to voltage or voltage to current. But you guys need to take note that if it's an independent source, then change it to an independent source. You can't change from maybe this a dependent source, voltage source to a independent current source. That is not possible. Okay, next we have Thevenin's theorem. Thevenin's theorem is a linear two-terminal circuit that can be replaced by an equivalent circuit, consisting of a voltage source, V Thevenin, in series with a resistor, where V Thevenin is the open circuit voltage at the terminals, and R Thevenin is just the input or equivalent resistance at the terminal when the independent sources are turned off. So here is the steps to finding the V Thevenin and R Thevenin that is available in this matter itself. So to find R Thevenin, we need to deactivate all independent sources because we just want to find the R equivalent that is in the circuit. That's why we need to turn off all of the independent sources, and then we just count the error total that is in the circuit. And for V Thevenin, we don't need to deactivate all of the independent sources, but we need to find the value of V Thevenin with node analysis or mesh analysis. And also here that is available in our PowerPoint is to find E load and V load, which is just the current and voltage value that is in this R load here. Okay, this is the example for the Thevenin's theorem. We have this circuit here, and then we need to calculate the Thevenin equivalent circuit from this circuit. So this is the solution. It's quite easy. First, we need to find our Thevenin. We just deactivate all of the sources, this short and this open, as you can see here. From this two terminals here, A and B, we evaluate the resistors from this point of view. So that's why we assume 4 ohms here and the 12 ohms here are in parallel. Then when they're in parallel, we just add it with the one that is in series. So we get 4 ohms in total for the R Thevenin. To find V Thevenin, we don't need to deactivate the sources, but we can just use Kirchhoff current law or Kirchhoff voltage law to find the voltage value that is within the circuit. So here we can use mesh or we can use node, and it has the same voltage value, so it doesn't really matter. So the finished Thevenin's equivalent circuit is going to be like this. As we can see, we have the voltage law is 30 here, and then we put a resistor in series, which is this 4 ohms that we got for the R Thevenin. And don't forget to draw the R load too from this equivalent circuit itself. Next is the Norton's theorem. It's frankly quite the same as Thevenin's theorem, but it's only in a different configuration. As you can see, it has an current source and a resistor, but it is in parallel. It's quite the same as the source transformation we saw beforehand. So we can find this, I'll solve this example. It's quite easy. You just deactivate all the independent sources again and then evaluate from this point of view. As you can see, we get 8 ohms and 4 ohms in series, and then we parallel it with the the 5 ohm resistors. Then we get 4 ohms. Then we find IN with mesh analysis or maybe node analysis, and then we get the current, the short circuit current that is available, which is here is 1 amps. That's why we can simplify the the circuit to just 1 amps with 1 amp current source to a 4 ohm resistor. And for the correlation between those two, it's just as simple as a source transformation, as I said beforehand. So here I use the Thevenin's theorem to make a Norton's equivalent circuit. As you can see, when I use V Thevenin to find the voltage that is available in the circuit, then I just use Ohm's law to change it to just a current value. It's the same as the Norton's equivalent circuit. So Norton's theorem and, Thevenin's theorem is the same thing, but it's just a different configuration where Thevenin's theorem is a resistor in series with a voltage source, And Norton's theorem is a current source that is in parallel with a resistor. So that's practically it for this module. I'm sorry if it's a bit confusing at first because English is not really my best language itself. If you guys have any questions, you can ask through my contacts that is available in Mas Dua. Or if you have any questions about the matrices that are in my PowerPoint, they are all available in the reference book that I'm going to put in the video description below. So that's it from me. Thank you, everyone.